excited to present to you our results and that you're all here. This is going to be a kind of static program analysis to do loop transformation. There's some elements of abstraction here, so I hope you find it enjoyable. This is joint work with Clément, Aubert, Thomas Seiller, Thomas Rubiano, and myself. My name is Neea, Rusch. And so my co-authors and I, we worked a lot on trying to do different kind of program analysis to look at resource usage particularly. And if you are in this space, you will quickly find that particularly for time, loops is the point in, or the place in the programs where all the interesting behavior occurs. And that kind of brings us to this idea of loop optimization. So let's say that you have some idea that you want to optimize your program in some way. And there are many different kind of loop optimization that you can apply. I have included here some general examples of what it could look like. So maybe you have a single loop and you split it. If you split the body of the loop, then that's called distribution. If you split the iteration space of the loop, then that's called splitting. Or you can also put things together, and that's called fusion. So many different kinds of loop optimizations. In this example, I have used, say, task X and task Y to represent some kind of block of statements that are doing some type of operation. And the way this kind of transformation is easy if you assume that tasks X and Y are independent, but where the things get challenging is if there are dependencies between these blocks of statements, and you have to think about maybe there's a control flow that something needs to be written before it's read, or maybe there's iteration dependency that's an operation depends on something that happened previously. So it's in the space of I'm trying to optimize a program. I have all these different transformations, but I also have to keep in mind all the dependencies of what's happening in my program, and then trying to find the optimal approach to what you hope to achieve. And there's no singular answer to sort of what's the best strategy. It depends on what you try to achieve. So in this work, we are presenting an algorithm, and this is to perform a loop fission or distribution. And we say that it's going to add parallelization potential in your program in previously uncovered cases. So specifically when I say loop fission, I'm talking about the transformation where we start with one loop, and then we split the body of the loop. And then parallelization potential has this idea that if we can identify in a program independent statements, then we can have the hardware execute those statements at the same time as the system resources become available. So what we are trying to do is increase those opportunities in the program. And conceptually, if you think about this, it's easy to see how we would add this kind of gain here. If you think about that, we start with one loop, then we split it, and we say run these loops in parallel, and then you're gonna have speed up the time that your computation is going to finish. It's going to reduce. So that's a high-level idea of what we're presenting. We make several claims in our paper about our technique. So the most interesting thing here is that the way we do this loop transformation is going to apply to non-canonical loops, which is the fact that you don't know how many times your loop will iterate. If you had a canonical loop and you knew exactly how many iterations it's going to do, it's a lot easier to do this transformation. So we're looking at a case specifically where you don't know how many times the iteration is going to repeat. We're specifically looking at examples with while loops, but you can apply it to any kind of loop. So it's loop-agnostic technique. Another thing is that it doesn't require a lot of structure from the program, which means that we can do this kind of transformation on a very high level, or you could go sort of further down in your compilation chain and do it on an intermediate representation. And the last sort of interesting property here is that this is fully automatic, so you don't need to annotate your program in any way. And the motivation for that is that if we think about there's all this legacy code written a long time ago, and we still would like to have the opportunity to leverage the kind of modern hardware that we have to run it faster. So This is one way we could introduce this kind of parallelization potential and improve those programs over time. Okay. I'm going to give you a very high-level idea of how this technique works, and then I will drill down to these individual bits and I'll give you an example, so we'll go over it. But in a very, very sort of high-level view, the first thing we need to do is we need to understand the dependencies in the program. And for that, we're going to use a special kind of graph. It's called a data flow graph, a DFGs, and I'll explain what that is. But using that DFG, we can then make a dependency graph. Then we make a condensation graph and determine its covering. So this is a graph-based algorithm. And then finally, from the covering, we figure out how to distribute the loops. Okay. So that is the high-level idea. First, let's start looking at the program. So I said that you could have a different kind of syntax, but generally we're looking at an imperative deterministic language. So in our paper, we talk about a while language. It's a very standard. It has variables, expressions, commands. One thing that we add that's a bit special is the parallel command. In terms of what the program is actually computing, you can have pure function calls, you can have arrays, you can have a loop carry dependency, which means that your loop depends on something that was done at a previous iteration. You can also have very complex termination and control statements there. One thing that we do not cover is if you have any kind of memory access within the loop itself, so if you have pointers, it may be the case that, so we're specifically trying to optimize loops. So if you have some pointers that are outside loops, that's fine. But specifically inside the loops, there should not be any memory or like pointer manipulation and things like that. All right. So let's imagine that we have our program. The first step that we need to do is we need to identify what we call in and outs and occur variables in this program. And this is a kind of abstraction we do. So I will consider the case of assignment. It's very easy to see how this would work. So if we think about what is the out variable of assignment, it's going to be the left-hand variable. And then the in variable are where the values are coming from. In case of an array assignment, we also consider the index as an in variable. And the occur variables is just a union of in and out variables. Okay. But I do want to say that this is an over approximation. So particularly arrays, we over approximate those. But it's not really a limitation because eventually when we go into parallelizing these, the array is going to be assigned. Every operation on the array is going to be specific to a thread. So it's okay. We'll have full control over what happens to the array. Okay. We represent these in and out relationships as a data flow graph. So I'm going to explain to you what that looks like in more detail. So a data flow graph, or DFG, that's a matrix over a fixed semi-ring. And it's going to represent the weighted relationships of these variables in a specific command. We have three different kinds of dependencies that we identify here. So you can have dependence, which we mark with an infinity. You can have propagation, which we mark with a 1. And then you can have the 0, which is reinitialization. And there's a relationship here where the targets of the dependency arrow, those are actually the out variables. And then the sources of the dependency arrow, those are the in variables. And then also reinitialization, those are out variables. For each command in the program syntax, we define how do you actually identify the in and out variables. So I have included here as an example an assignment. I said assignment is fairly easy to see what will be in and out. So we consider it a dependency if you have one is the out and one is the in. And then it's a 1 if x is equal to y, the x variable is equal to y, but it's not an out variable, and everything else is a 0. Okay. And then we have in the paper, we have defined how to determine all of these relationships for each kind of statement that our syntax supports. Once you have your in and out variables, you can represent your dependencies graphically. So what we want to actually create is this kind of matrix to show the dependencies. We can also make a graph. So that's a weighted bipartite graph to kind of visualize how the data flows in the program. There is one more thing, though. So if we make the DFG, when we look at the individual statements and we look at the dependencies, what that's not yet accounting for is the potential control expression of the loop. It could also be the control expression of an if statement. So we need to add a step to account for the impact of the control expression. So we do this in a step that we call correction. In the correction step, you consider what are your control variables what are the variables that occur in the control expression. That gives you a vector. Then you consider what are the out variables of the body of the statement, and that's another vector. You multiply those, and that will give you the correction that we apply to the DFG. That in itself, that completes the construction of the DFG, so we can look at what are the next steps. So in our actual algorithm, which we present in the paper, we say that, okay, you're going to have a DFG, which you have computed, and the algorithm proceeds as follows. You're going to build a dependency graph. Then you build a condensation graph from that, and then you compute the covering. And the covering gives you the way to split into the loops. So I'm going to explain these in a little bit more detail. So for a dependency graph, I want to illustrate with an example. So I have here on the left is a sample program with a loop, the W. And if we did all the steps to compute the DFG for that program, we would end up with the matrix that I have illustrated in the middle. And then what we need to look at is, remember, we have in and out variables for different statements. So statement-wise, we would look at what are the input and output variables to build the following graph. In the graph, the statements are vertices, and then we need to determine if we should draw a directed edge between the statements. It's going to be if we have an in variable and an out variable, and it happens to have an infinity in the matrix. So if we look at the variables I on the vertical, I mean the top row, but vertical, you see I, and then the I on the horizontal, there's an infinity. And because we have that pairing, we would make a directed edge from between the first and the last statement in the program. So, and you would do this for all the statements in your program to actually build this graph. But that will give you a dependence graph. The condensation graph is a simplification of the dependence where we do strongly connected components. And then to compute the covering, so covering is a collection of subgraphs. And there could be multiple ways to do a covering of a graph, so we need to restrict that a little bit, say particularly what kind of covering we're looking for. So we're looking for a saturated, to say that we're considering specific edges, and then we say it needs to be proper, so we're restricting how do you pick the subgraphs. And so we need, in overall, it needs to be a proper saturated covering of the condensation graph. Okay. From the covering, we then determine that here's a loop. If we may find multiple subgraphs in the covering, so if there are multiple, then we split. We reconstruct the original program with these multiple loops, and then we can parallelize this. Okay. So that is a technical description of the steps, and that's a bit dense. So I'm going to illustrate all of this with an example. I think that this will illustrate it to you better. So like I said, we start with, if we have the program on the left, we start with identifying what are the in and out variables, and we would go in a look at each command individually first in the body of the loop. I have included their example, a few of them. So you'll see that they're all assignments. So we're looking at the variables on the left to get the out, and except the array index, that's in variable. And sometimes you have this kind of circle, like with the S, that it can be both in and out variable. Okay. once we have the in and out variables, remember we need to build a DFG. So I have here demonstrated what a DFG would look like just for command 1, so the first line in the body. You'll see I have my propagation on the diagonal. I have my dependency along the vertical, and then x doesn't refer to itself, so there's no dependency at xx. If we analyze every single statement in that program, and then we apply the correction, which accounts for the control of the loop, trust me, you will end up with this matrix. So this is a representation of the entire program that I'm analyzing now as a form of DFG. And that gives me the dependencies that I have between the various statements. And here's where our interesting stuff starts. So using that matrix that I just showed, I would build my graph. And I would say, here are my vertices. They're the different statements in my program. I'm going to figure out where I connect my edges using the matrix. And specifically when I have the infinity in the matrix, that's where I connect. So I would get this graph for this program that I'm analyzing. And the next step is to do a condensation graph, which is a strongly connected components of what I had previously. And then figure out the covering. So it's very simple. It's splits in 2 ways. I end up with this kind of partition. And from there, I can reconstruct my program with 2 parallelizable loops. And so this is a fairly straightforward example to demonstrate what we're doing here. And it may seem a little bit like a toy example, but it's actually a real example. So this is a part of a bigger example that we present in our benchmark. So we didn't just come up with this technique, we also measured it. And it consists of several examples like the one I showed before, but in a bigger setting. We made an artifact where we analyzed various different programs. We applied the transformation. In this example, we mapped our syntax to C programming language. We used OpenMP directives to do the parallelization. We looked at different programs from different benchmark suites. So there's a bit of a challenge in doing that because a lot of the benchmark suites that exist, they're designed for canonical loops. And we specifically said that we want to look at this kind of example where we have non-canonical loops and we don't know the iteration space. So we took part of them and we converted them to while loops to actually test what that would look like. And then we had fixed our experiment parameters in a way that we wanted to look at C. We wanted to look at the loop fission transformation. And then there was another thing that we wanted to see how this tool would transform this program. So considering all those options, we needed to find a C-based source-to-source compiler that does loop transformation. So we found one tool that does that exists. So we considered that as our comparison target to evaluate how is our method different. And so we measured all of this. Our benchmarks show that we're able to transform programs that the alternative tool would not transform. So that's the interesting property of being applicable in the non-canonical case. Then we measured specifically, I have on the top half results of some of the while loop experiments because what we found is that the performance of your while loop optimization actually depends on the number of times that you can distribute the loop. And that's a semantic constraint. And then for the for loop, if you are parallelizing those, you get the same kind of performance as you would get with the alternative tool. Another aspect that we did here was we did the insertion of the parallelization directives automatically. So I mentioned briefly that we're trying to actually create a practical method also. And then we say that you could automatically inject these directives. And we did this kind of automatic injection during the evaluation. So this is this is possible. One thing I will note that if you wanted to insert parallelization directed to while loops, this is still an open sort of challenge because, for instance, OpenMP doesn't support injecting those while loop parallelization direct. So we explain in the paper how we did it. But yeah, we have done a lot of experimentation around it, so we know it's doable. All right. So just to recap what I have presented here is our loop transformation method, which you can apply to all kinds of loops in imperative programs. If you're interested in the correctness proof that makes sure that our transformation is preserving the correctness of the program, then I encourage you to look at our paper. You should also have a look at our artifact. It's very nice, and it's open source. That's it. Yes. Yes.
Thank you for the nice talk. As I noticed that a lot of your co-author come from the complexity program complexity analysis.
Yes.
I was asking, can you use parallelization technique to obtain upper bounds on the complexity of programs or to improve the existing ones?
Okay. So the question was, can we use this to improve complexity? Yes. So as a side note, so the dependency, the data flow graph analysis that I showed earlier, this is in fact reusable. And the two Thomas have used it before. They used it to do a different kind of program optimization, and that was to identify quasi-invariants. And in that case, what they did, if they found a nested loop, they could peel or hoist that loop from outside the loop, and that would reduce the complexity of the program. So you can find alternative uses for this kind of dependency analysis, and you can apply in different ways, specifically to target those properties also. Yes.
Yeah, so I would like to know about the language features. Like, for instance, if you have pointers, did you consider the case where you have pointers that can create aliases? So did you look into that and say use a conventional pointer analysis, or did you not consider it? And then I had the second question is about arrays. So you did show a very coarse-grained handling of arrays in the example. Did you also consider finer-grained handling where you would just try to have dependencies across various cells of the arrays, like with indexes properties?
Okay. So let me start with looking at the pointer memory. So a bit of the challenge of why we exclude pointers is because if you're doing operations in memory, we would not necessarily know how the data is flowing in that case. So at this point, we exclude pointer. It would be an extension of the method to extend it in ways that we would know how to analyze those completely and be able to make the guarantees that you are indeed preserving your semantic correctness as you do this. Same with if you have function calls that do something on those variables. So that's why we restrict the syntax to say you can only have pure function calls, like functions that do not modify your input variables. For a more fine-grained analysis, so depending on how you split your loop, if you had multiple threads that operate on the same array, then you have this scenario that you have to be really careful how you distribute this across the different threads. In our system, what we're doing is we're splitting in a way that if you're the thread that is assigned to operate on this array, you get full control over this array. So you can do all the operations you want, but you would not end up in a situation where another thread would work on that same array. So I'm trying to think of if there's a way to sort of mix that, but I don't have an obvious answer for you, but that would also be something that would be an extension of doing that. Yes.
May I? Okay. I was wondering if right now I think your approach, from what I've understood, is oriented at finding like independent sets of operations. So you assume that your loop can be split into completely independent, let's say, sub loops, let's say, that can run in parallel.
Yes.
I was wondering if you are considering the possibility of having like piecewise independent operations that then when you perform, and then you may synchronize after that, and then you split again, and then so on and so forth. So like a generalization where if you at some point have to combine the results of some independent operations,
Yes.
you don't just throw everything away, but you just do these independent operations in parallel, and then you join in some way, and then you split again, possibly. Something like, I don't know if I'm being clear, but yeah.
Yes, I've seen this concept. It comes up a lot in the parallelization examples called a reduction, so that you would do this kind of computation and you reduce to a total at the end. So if you had this kind of scenario, what I can say is that you would have to find a way to perform the operation in a way that you could do it independently in this case. And our technique may not be the optimal case for that. What we really want to say is that the intent is not to say that we have this kind of solve all problems kind of algorithm. It's to say that you could combine this with an algorithm that does that very well. And then you have sort of best of both worlds. And think about this more of a global strategy of how do I want to optimize my program, and how do I want to transform it so that I get at the end the kind of optimization that I want in a global sense.